Hey guys, so in this video I'm going to try to clear up some of the confusion that comes from studying systems in energy conservation equations. This can definitely be confusing, but the better you understand this, the better you're going to be at doing conservation of energy problems, and in the end, the better the exam is going to go for you. So I'm hoping this video will take a pretty simple example and allow you to see how you define the system and how if you define the system differently, as long as you do the right thing, you'll get the right answer. So I'm going to start with our conservation of energy equation. This equation is that the change in energy of the system is equal to the total energy transfer from multiple sources. And if you recall, the textbook expands this as the following. That the change in the energy of the system is the change in the potential plus the change in the kinetic plus the change in the internal energy equals the work. This is what I am really considering to be our conservation of energy equation. And hopefully I'm going to sort of elucidate some of these things which might be a little confusing to you, like this internal energy and like this work. So what I want to do is I want to do the same problem, different systems, and get the same answer. So I need to pick a problem, and this is going to be the problem we're going to do. How fast is a basketball falling if you drop it off a building? So I'm going to give you building height later and the mass of the basketball and things like that, anything we need. But this is the problem which I want to do two different systems for and show that you get the exact same answer. So system one. Systems are composed of objects. Systems are not composed of forces. They are composed of objects. The objects which I want to be in my system for this basketball problem are the basketball and the earth. So, to illustrate my system, I'm going to do a couple of free body diagrams. I think that this is generally a very good idea, although for energy problems, free body diagrams are actually not required and are not as useful. But I think a picture here is a very good idea. So, this is what I'm going to write. I have one free body diagram which represents my basketball. That's the force of gravity. I have a second free body diagram which represents the earth. That force is the same due to Newton's third law, and of course the earth is huge, but free body diagrams are only dots. So it doesn't matter how big the earth is, it's still just a dot in my free body diagram. And then what I'm going to do is I'm going to draw dashed lines around this thing. And that thing is going to define my system. Everything is inside the system, and therefore this is an isolated system. There are no forces in and out, isolated. Everything outside the system is the environment. That's everything outside here. Okay, so if I write my conservation of energy equation, I have no external work being done because the system is isolated. I have no internal energy change happening, and so I have only a change of potential energy and a change of kinetic energy. So it looks like this, so I'll expand that. So here's my change in potential energy. That's the potential energy of the system. The m is the mass of the basketball. Here's the change in kinetic energy of the system. Again, mass of the basketball, velocity of the basketball. So some of these are going to be 0. If I drop the basketball from rest, that means the initial velocity is 0. And what I want to do is I want the basketball to land. I want it to land some at the floor, and so my final y is going to be 0. So here's my conservation of energy equation after I put in the specifics of the problem. The change in potential energy is negative because it's going from a high value of y to a low value of y. And the change in kinetic is positive because it's going from 0 to some positive value of the velocity. And so I can solve for the velocity of the basketball. And it's pretty simple. It's just that the final velocity is the square root of 2g yi. So just because we can get some numbers in there, we can use the Empire State Building. The height of the Empire State Building is 443 meters, and so that gives me a velocity of 93 meters per second. So that's pretty huge, and actually the real value would be a bit less than that because of wind resistance, but that's okay. That's not the point of the problem. We're just trying to see if we get the same answer by picking a different system. So let's do that. So the system I want to pick now is ball alone. So the only object in the system is the ball. Free body diagram plus a system boundary is the following. Of course, I can't actually change anything about the free body diagram itself. That is specified by the physical problem, which is gravitational force acting on the ball. But I can specify the boundary of the system, and I've specified the boundary to be just enclosing the ball, not enclosing anything else, and that means that I have an external force. The external force is the force of gravity. Okay, so here's our conservation of energy equation. Let's make sure that we understand what terms are going to actually go into this. We're certainly going to have kinetic energy. The ball isn't moving at the beginning, but we certainly know it will be moving at the end, so it will have some velocity later. But what are we going to do with the gravitational force? Well, now Fg is external. When you have an external force, remember that this entire thing, this is the change in energy of the system. And Fg is actually acting from outside the system. It's acting on the system, but it's crossing the boundary. So really, it doesn't belong on this side of the equation anymore. It really belongs over here. So in other words, the force of gravity is doing work. So that term is going to have to be in here. So what else do we have? We don't have any internal energy. I know you guys don't really understand what the internal energy is. I hope that later in this video you'll get a clue a little bit. But for the moment, we don't have any change in internal energy. And so what are we going to do about this potential energy? Well, we have some potential energy, it would seem, because we have gravity. But remember that this is the system. We don't have any potential energy due to gravity because the Earth is acting through gravity outside of the system. The Earth is outside the system. This is just some force acting on the ball. You can also think of it like we're going to put that into W, so you don't want to put it in two places. There's not going to be a change of potential energy and the work due to gravity. It is either going to be the work due to gravity or the potential energy due to gravity. And because we're external, it's going to be through the work. Okay, so let's write that down. The change in kinetic energy is just as it was before, 1/2 mvf squared minus 1/2 mvi squared. We're going to put the work due to gravity here. The work due to gravity is mgh. A slight aside, where the heck does this thing come from? I've been writing the work due to gravity is mgh on a lot of whiteboards, and a lot of people don't know where it comes from, and that's because it's actually a little bit complicated. Really, what I'm using is the fact that the work is the change in potential energy. It's actually negative the change in potential energy. So when I wrote the potential energy due to gravity in the last slide, I wrote mg yf minus yi. But if you want to compare yf and yi with the height, you can see that actually the initial y, that's actually the height. And the final y is 0. So this negative sign right here and this negative sign right here cancel, and you get mg times h. That's where the work due to gravity comes from. It comes from the work in any situation for any force is negative the change in the potential energy. Okay, well now we can just continue and solve the problem. The initial velocity is 0, so our conservation of energy equation reduces to the following, which you can rearrange to solve for the velocity. Square root of 2gh. So this is the exact same expression we got in the on the first slide, except that now h, of course, yi is h now, but as we talked about over here, that's exactly what we expect. So check. That is the exact same expression. We used a different system, and because we used a different system, the force of gravity, which was external here, showed up in the W, whereas in the first system, because the force of gravity was internal, it was the potential energy. So that's great, but what about friction? Friction is what we're studying in class, and we really need to understand how friction goes into this, this scheme. So I'd like to do an example with the same thing with friction doing two different systems. So I've got a block sliding on a sticky table. How far does it move? So the first system might be the first thing that you think of. I'm just going to have a system consisting of the block. Okay, so I'm going to give a free body diagram for that. So I've got my normal force, my gravitational force, the force due to friction, and I want the gravitational force to be an internal force to this system. That's really the best practice. As you saw on the last slide, it can be a little confusing about whether that gravity should be work or should it be delta U. I want it to be delta U, so I'm also going to add in the Earth. And then I'm going to put my dots around it so I know what my system is. Okay, great. So I have two things acting external to the system. That is, I have Fn and I have the force of friction. I have not included the table as part of my system at all, just the block and Earth. So the first thing to notice is that Fn isn't doing anything from the perspective of energy. So we can actually forget about Fn for the moment. But of course, force of friction is changing the energy of the block. Here's my conservation of energy equation. I can get rid of some terms immediately. I'm certainly going to have some change in kinetic energy. I'm certainly going to have some work done because this force of friction is external. I don't have any internal energy, and I shouldn't have any change in potential energy either, because the block is moving horizontally. It's not changing its height in the gravitational field. So here's the change in kinetic energy. I want to set that equal to the work due to friction. Well, so what is that work due to friction going to be equal to? I'll write this out in the most general form because you're going to have to be able to do this on the exam. The work due to friction is the force of friction times the distance the block moves times cosine theta. Here, the block is sliding on a sticky table, so I've said that it's sliding in this direction. Cosine theta is between this direction and the force of friction, 180. So you get a -1 from cosine theta, and this is just going to be negative force of friction times d. Of course, in an exam, I could give you all sorts of different forms for the force of friction. Maybe you might need to write Ff equals mu Fn, of course. That's definition of force of friction. For the moment, I'm just going to leave it as Ff times d. Okay, so now let's put that into our conservation of energy equation. Right there, and now notice that we want the block to move and then stop because we want to know how far it moves. So the final velocity is 0. We have only initial velocity. Check to make sure our signs work out, which they do. Negative sign there, negative sign there. So we can solve for the d. And we get d is mv squared over 2ff. Sorry, this is the force of friction. My screen gets a little crappy when you write at the bottom. So this is the distance that the block travels as it slows down due to the work being done by friction. Now, I'd like to repeat this calculation using a different system to see if we get the same answer. So the next logical system we can try to use is try to make it isolated. Try to put everything you possibly can into the system. So that means block, that means Earth, and that means table. So let's give some free body diagrams. All right, so I've got my block, which has normal force, frictional force, gravitational force. This is the Earth, gravitational force matching that gravitational force. This is the table. Normal force equal and opposite, frictional force equal and opposite. Going to put some dots around it so I know what my system is. All right, cool. Here's my conservation of energy equation. So what terms am I going to have now? Still apparently no change in potential energy. There's no springs. The Earth is not moving the block in the vertical direction, so that seems pretty safe to say it's 0. Kinetic energy. Certainly going to have kinetic energy because the block is certainly moving. Now work and internal energy. So the work happens when there's external forces on the block. External forces happen if there's no Newton's third law pair in here, but every single force has a third law pair. FF, FF, FN, FN, FG, FG. Everything is paired up. There's no external forces whatsoever, so we're forced to conclude that the work is 0. So what is going on with the internal energy? Well, in this case, we have an internal force. Here it's the force of friction, which is going to be changing the energy of the system. We know it's changing the energy because the kinetic energy is slowing down, so there must be a change in energy here, and in fact that must be due to the kinetic friction. It's an internal force now. It's changing the internal energy. How much is it changing the internal energy? Well, friction does work, so it's actually changing the same amount of energy as it does work on the system in the previous case. So there's that expression. So notice a few things about this kind of strange result. Number one, it's positive. It's positive because the energy of the system is increasing due to the change from kinetic energy into the internal energy. So the force of friction is increasing the energy of the system, and in fact, that makes sense because it's heating the system up. It's changing the energy of the system by raising the temperature of the interface between the block and the table. If you don't like the fact that I'm writing this down and you don't know where it comes from, you can check out the discussion on page 205 of our textbook, where he shows why he's calling the change in internal energy the force of friction times distance in the positive manner. We don't need to go into too much detail on that. You can either think of this as this is a result, when there's friction on the system, the change in the internal energy is the force of friction times the distance. Or you can also think of the fact that this really is doing positive energy on the system because it's increasing the temperature of the system. Before, it was external to the system, so it wasn't doing anything but taking energy away from the block. But now, the block and the ramp together are increasing in energy. Okay, so I'm going to put that in and solve this, the rest of this problem pretty quick. Here's the conservation of energy equation with the friction in there. The final velocity is going to be 0. So again, we're just going to solve for the distance that it travels. And as we expected, we got the exact same answer. So, a couple of lessons from this. One, picking a different system, as long as you do it consistently, as long as you work out your conservation of energy equation carefully, you will get the same answer. So picking the system is your choice as long as you stick to your choice and do the right thing. The other thing is that picking a system and writing down the conservation of energy equation, really this just amounts to juggling negative signs. So here you noticed that the change in energy became positive right here due to the force of friction, where before the work was negative. So it's just a different interpretation. You can think of the ramp and the block together. That system together is increasing in energy because the friction is creating some thermal energy. Or you can think of the friction separate from the block, slowing down the block, doing some work on it, and decreasing the block's energy by itself. But from an energy perspective, that's just juggling around negative signs. So, several lessons you take from this. I hope that it's been clarifying. I'm going to expect you to understand systems on the exam, but of course the number one thing is to get the problem correct. So I hope that you can take this information and try to make it internal and try to understand it as best you can. And I think it's going to be helpful on the exam to have these kind of systems in your head. All right, thank you guys.